give a little bit higher grade overall in terms of quality and things of that nature. So that should help significantly. I will attempt to keep an eye on chat. Okay, so I'll try and do that. So yeah, that may work. All right. So welcome. We're going to try and get into chapter 10. This is kind of the summary refresher on chapter 9 and what's involved. Phase diagrams, you guys have talked a little bit about, and understanding what the composition is of each phase, looking at weight fractions. Those are really an important distinguisher, as well as the temperature for a particular composition, what that temperature means. And what we're going to start getting into is some of the information from the phase diagram, but also how for a given composition, we sort of take a slice of that. If you think of a 2D graph, but in 3 dimensions, like a lot of individual versions of those 2D graphs, for each different composition, there's also a temperature time graph. And so we're going to look at some of those as we get into this particular chapter. So there's a lot of things that start leveraging some of the principles that you've learned about microstructure, and that's why these two are together. And it flows into what we're learning in chapter 11 as well. So somehow in the next couple of weeks, we have to get through all of that, going all the way back through chapter 10, and then we've got some labs in there as well. So a lot of things going on. There's a lot of material we're going to be throwing at you. And what I may do to try and kind of double up a little bit so that we can get caught up is I may go ahead and have make sure we try and get through. We should be able to get through the rest of 10 today. We might be able to start getting a little bit into 11, but that way at least you guys will be able to get started on the work for 10, and you'll have this as a reference point. So and I think she had already posted the slides for 10 for you guys, so that way you have what you need. So that should kind of put you off to a good start. All right. The key things from this particular chapter 9 that are going to carry over importance into 10 and 11 are the eutectic, eutectoid, and paratectic points. The eutectic especially because that gives you a sense of the lowest temperature at which a composition will actually melt, right? So it has everything to do with the temperature at which a phase transition happens, and where you cross the boundary into a phase envelope. So there's a lot that goes into that. A couple of the other things that we'll cover in this chapter are going to be understanding what kind of this process looks like. So we have the eutectic point here where the E is. You have some kind of alpha phase, some kind of beta phase. So pure alpha phase envelope. It's just a fancy name for this line. The envelope that contains that phase pure in any given for any given composition at those temperatures, you cross into one of those crystalline types. So alpha plus liquid, beta plus liquid. This eutectic point tells you there's some amount of liquid above that temperature always. So around 800 C for this, which is looks like silver copper alloy. So a lot of the cheap rings and things of that nature are made of something like this, some composition. So above this line, you start getting some degree of melting. You'll have preferential melting depending on the composition of which one is there. So fairly easy phase diagram to understand overall. Before we get too far into that, anything like super unclear about phase diagrams to you guys at present? And I have chat up, so I'll be able to see that as well. Or are you guys feeling sort of comfortable with basic phase diagrams?
Feel like we felt pretty good. They were on the last quiz too, so.
Okay. Yeah, you guys should have seen them enough that they're not necessarily like scary still, but there's still a lot of information contained there. So yeah, there's the solidus line, the solvus line, which is getting down into all of these things. So we're going to transition now into the phase diagram, and we're going to bring in carbon into the iron phase diagram, so it gets to be a little bit more complicated. Yeah, gratuitous cartoons from newspapers or something like that. The snowman may be far side, I'm not real sure. But the idea is we're going to be covering a lot of covering a lot of helpful information about steel. A lot of engineers have it in their head that there really are only two materials to build stuff out of, steel and aluminum. There's really a lot more than that, but we're going to focus on how to understand steel and different grades and types, different microstructures and grain structures that promote different kinds of behaviors in the material itself. The processing also has an impact on that. So this is some of what we're going to be covering today. And especially understanding elements of what are the hypereutectoid areas, hypoeutectoid. So taking advantage of understanding what happens above and below. Some of these different microstructures that have different properties are going to change how the steel behaves, right? So we used to, years ago, make a lot more things out of inexpensive steels that have different kinds of properties, and we'll cover some of the different grades of materials. They have a lot of similarities because they're similar in chemical composition. There's only minor differences in terms of the weight percent, but that greatly changes how they behave, especially in terms of the processing, which we'll get into more in chapter 11. So this is kind of more just what the materials are and what the structures are, and then we'll look at processes and changes to those in the following chapter. So alpha iron or ferrite, body-centered cubic arrangement. There's a limited solubility of carbon there because it's not very permeable compared to the face-centered cubic where austenite is. So this is the reason why a lot of times you have to heat the material up to such a high temperature in order to allow things to move, right? Because you think of the way that metals are structured, they're crystals, but they still are solubilizing some of these different molecules like carbon. So you have to heat them up to these really obscenely high temperatures in order to give them enough kinetic energy that you start to get molecular movement from these crystalline structures. So they still follow the chemistry rules that apply to other kinds of materials, but they happen at a much higher temperature because those bond strengths are significantly higher compared to some of the other types of materials that we have, and their mass typically is fairly high, and that means they require that much more kinetic energy, higher temperatures, in order to make them move around and improve their kinetic energy to improve solubility. So the iron carbide phase fields are what we're going to be spending a lot of time in, and so a couple key definitions there are the ferrite. There's alpha and then gamma. Both of those are body-centered cubic. Gamma is face-centered cubic, and then like I said, that one has better solubility. Cementite is iron carbide. So that's the nomenclature for it. So this is a section of the phase diagram, and this will give us a couple key points. So the gamma phase is way up at the top there, very high temperature, very low carbon content. It exists only in a very narrow region. The austenitic or austenite range for gamma is where we start seeing some changes in terms of being able to harden materials when we melt up into that phase. So above that 1100 range, we don't have to go quite that high to start reaching some of the differences. You'll see that actually somewhere around that 800 range, because we're passing this eutectoid point. So this is that melting temperature at which we start to see an actual phase transition, right? Versus the eutectic point, which is here. We start to see the alpha change to gamma, and this is where, as we start that recrystallization process into gamma, we change the orientation, we can change mobility of carbon, and then because of that, we can change the kinds of grain structures that are going to result when we cool this down. So there's a lot of pieces and parts involved there. So the eutectoid is about 727 C, and the eutectic for iron is this about 1100, 1148. This is where you're going to have a couple different types of phases occurring, and both of those are important. This eutectic point is right at 4.3 weight percent carbon, so that will be important in some of the later processes, especially as we're making things. So you'll see later on that a lot of the steels are in this lower range, lower carbon. Then there's high carbon steels, and then above that is our cast iron range. So what do you guys think the eutectic point here is most commonly used for? Why would it be useful to have a pure liquid for some iron carbon mixture if that's in the cast iron range? What do you guys think that's useful for?
It would change to a more even consistency, like it would all happen more quickly.
Yeah, you can actually get the material to flow at a much lower temperature here around 1200 versus needing to be up around 1600 for some of the steel compositions, right? So how often have you seen something actually made of cast steel versus cast iron? You probably haven't seen a lot of cast steel, right? Because in order to cast something, you have to melt it down into a liquid, right? You see people all the time casting molten aluminum, right? And we'll get to that phase diagram later, but aluminum is molten somewhere around something like 600 to 700 C is also the same range where materials become emissive and start glowing red. That's really, really important for some of these aspects. So the liquid up here at higher carbon composition, we're out of the steel range, we're now into the cast iron range. So this lower melting temperature makes it much easier to cast iron, which is why we call it cast iron from the iron phase diagram. We add enough carbon in that we can cast it at a lower temperature. So we don't have to heat things up that extra 400 degrees C, right? Because imagine trying to get to those really high temperatures, just trying to burn logs on a fire. You're just not going to reach obscene temperatures like that very easily without having some kind of a crazy blow-through forge, and then you have to have somebody continually moving air through that forge, and it creates all kinds of. So a lot of cast iron is going to land somewhere in this 4.3 range of weight percent carbon because of that. So this is why these phase diagrams are important, because it gives you an idea what the material can do, but also what kinds of processes you can do at some of these different temperatures. So that eutectic point is right where you go from liquid back and forth across that line, depending on the temperature. It's at that composition. You have gamma and iron carbide, whereas the eutectoid point, you go from back and forth between austenite and alpha, and so alpha ferrite and iron carbide or cementite. So they're in gamma grains. When you go down below that, the ferrite is soft. The cementite is very hard, which is why it's named cementite, right? Makes sense. So that's what forms some of those zebra stripy patterns. And so combining those gives you a material that is very hard to smash, right? You think about something like a phone book or something that has a lot of stacked layers, and the behavior of that when you try and compress it or bend it, it is sometimes compliant to bend, but if you're trying to shear it or tear it, it's very non-compliant, right? Things with a lot of stacked layers tend to resist force much better than things that are stacked. For instance, like in this phase, these might be arranged more like marbles or blocks that can slide past each other. The cementite makes it very hard for those grains to move, which makes for a harder material. But there's some spring and resilience to the material because of the alpha phase that's still there. So the different ratios change how those behave. And so this is kind of what that grain pattern looks like, which is why I use that kind of phone book analogy, right? So you have some kind of grain boundary here, another one here, maybe another one here. And this one probably is somewhere around here. So these grains themselves can move past each other with great force, but the grains themselves don't want to be compressed any harder. So this is what's called perlite, and this is a very, very hard phase. So at a sufficient composition, you get these zebra stripy patterns that are very resistant to being crushed and smashed. And that's what makes steel so durable, is these grain structures. So the hypo-eutectoid steel means it's below this eutectoid point, right? So below 0.76% carbon. So that's an important number to at least recognize. This will give you some additional range to work in. It's also a little bit above the pure alpha composition here, so it's not actually really all the way to zero. It's something like 0.1%. Or something like that. So above that range where you have these two phases, it's still steel. Because if it has 0% carbon, it's just iron, right? And you're just going to have ferrite. You're not going to have anything else. So it has to be above the zero concentration.
Your mic is muted, Professor Stocks.
Shouldn't be. Interesting. It is trying to key in on hotkeys, which is fun. Let's try that again. So you start with at a higher temperature, so above like the 1,000 degree C range, you start with these gamma grains. So this is the austenitic phase. As you start cooling down and reaching that phase envelope, heading toward the eutectoid. You've got this region defined because we're talking about a hypoeutectoid steel. We're below this range. We're below the eutectoid range, but we have to be above that 0% because otherwise that's just iron. So it's something like 0.01 or 0.1% carbon. It's no longer just pure iron in the ferrite phase. So this is that hypoeutectoid, so below the eutectoid point steel. As you cool this down, you start getting nucleation of these alpha ferrite grains. And then you start getting into as you cool down further, you get inside this biphasic envelope. So you get alpha and gamma together. And then as you go a little bit further, you can get into the perlite region. So you get perlite forming because of stratification that happens, and the degree to which you form perlite from these gamma grains is from the austenitic phase is dependent on the path that you take, but it has to be below this 727. So it has to be a temperature below the eutectoid point. So whenever we're hardening steels, we have to take it above this eutectoid point, usually up around 800 to be sure. That way we're definitely getting the sample up above 700 C, and then cooling it back down so that perlite can form. That's a necessary part of hardening the steel. And that's why the hypoeutectoid is so important. So this is what that grain structure might look like. Depending on the specific weight percent of carbon, you can have more perlite or less. But the formation of perlite is really, really important for something like a hypoeutectoid steel so that it can be hardened and used in end applications. There are others where you might need more depth and detail to understand how these ferrite grains interact, but these are what are referred to as proeutectoid ferrites because they're a result from this pass through that eutectoid temperature. So when you change that just a little bit, you change what the end microstructure looks like. So you have R and S type, and we'll cover a little bit more about that, I think, a little bit later. But the key to really understand is the weight fractions here. So this is going back to your lever rule and applying these principles, right? So you have a weight fraction of alpha and a weight fraction of gamma. So you guys should sort of recognize these formulas, or at least recognize that they're there. And because the two weight fractions have to add up to 1, you really only have to solve for the alpha weight fraction to get the weight fraction of gamma that's left. So this is dependent on the composition and where it is on that tie line for using the lever rule, right? So that still is going to apply for all of these materials, and that's where these formulas are going to come in helpful, especially in the problems that you guys are going to be doing. Once we get into chapter 11, most of those questions are going to be more qualitative rather than quantitative. So there's still some quantitative questions, I think, for 10, but not as many. There's a lot more in 10 than there are in 11 from what I've seen, because we're focusing a lot on grain boundaries and interactions, processing, and what that does. So a lot of that is qualitative by nature. So perlite is formed down below that eutectoid point. And so here you have a new tie line where again, R and S are used. And this, so you can tell kind of what the weight fractions are going to be for those. Similar kind of approach, same formula, S over the sum of R and S. Basically all phase diagrams that I'm aware of, especially with multiphasic envelopes, generally follow the same kind of process. So when you're trying to figure out what's the weight fraction of carbide, you just need what is the weight fraction of alpha prime, because whatever's left in gamma after the alpha is taken out, that's what will become perlite, and this is how we determine it. So there's a couple steps in the lever rule. Does it make sense to you guys why this has to be this way?
Yeah.
Because it's just a mathematical necessity as we're following this cooling line for a given composition, right? Because if we're cooling it down, it can't suddenly change composition, right? It has to follow this line down, and so we have these two different areas above and below the eutectoid point that we have to watch. So this should be the same kind of thing that you were doing for chapter 9, but we're going to do that for iron carbide now, and that's why this phase diagram is so important. So hopefully it's not too awful repetitive for you guys. Change the composition, and now we're into the hyper eutectoid steels. So this is above that eutectoid point in terms of composition. So the eutectoid point in terms of temperature is the same. So you're still forming austenitic grains. So you're still carrying it up in temperature, but now at the higher carbon content, you have to heat it a lot hotter, up around 1000 C, in order to actually get into the austenitic phase and then allow the same process. So this is between here about 0.76 and I want to say it's like 2. Austenitic is around, I want to say like 2.2, something like that. So same deal, we heat it up. As we cool it down, we start getting these small grain nucleations for this particular composition as we hit that phase envelope. So then we get a combination or mixture of the two, and same deal. So it's still iron carbide. We're just representing it, or here we've actually got not just alpha, but we have iron carbide. So we don't have alpha yet because we're above the temperature at which alpha appears because of our increased carbon content. So this is cementite. That's why we're representing it in a different color here, because it is a different grain structure. So now you have cementite and perlite, and this is why these higher carbon content steels are very much harder. So you can see the perlite grains, and you can see the proeutectoid iron carbide, so the cementite in these regions. So this is depending on the grain size, this is a much harder steel than the one we were looking at over here. There's a lot more resistance to movement of the grains in general, even if they're a little bit larger grains. We'll talk more about controlling grain size in the implications of processing and things in chapter 11, but it all ties together with what we're discussing. So you get perlite formation. So at this point, we have iron carbide. We're going to use, it's the same principle. So in this case, we're just changing the algebraically slightly, but it's the same formula. X over the sum of the two for the tie line rule. So typically X is going to be considerably larger than the weight fraction of iron carbide is whatever's left from this. So same deal, we go down in temperature in order to understand how much perlite is formed. We figure out where that is, and draw our line down, and we get our composition down here. We get our composition over here, and we get what our results are. So this allows us to then, as we get down below that eutectoid temperature, we can look at what our tie line looks like here, so that we can use this lever rule again. It's the same kind of calculation. We're determining the perlite based on whatever the weight fraction of the austenite is. So we get the weight fraction for alpha, what is just ferrite, by figuring out what the two are together, and then subtracting alpha from this. So we can figure out exactly what our end result is, right? So these two are not going to be the same. That's why we have prime. Same thing on this side of things. When we're looking down here, we're not going to have exactly the same weight fractions for the alpha versus carbide. It's going to be different than what it was up here because of where the phase lines are. It's going to be, because of kind of the symmetry of the alpha phase envelope, it's going to be closer to even on this side than it will be on this side for the higher compositions. And that's why there's such a small amount of iron carbide actually resulted compared to the amount of perlite, which is going to be a lot higher the more carbon you have. So does that make sense? All right. Another thing that we do is bringing in other elements for this. So we have, for a number of different kinds of applications, number of different reasons, alloying gives us lots of different kinds of properties. So if we've already got iron and carbon and we add in a lot of chrome or something like that, we start getting into stainless steel. Depending on what other things, you guys have probably heard of a chrome moly steel, right? So chrome and molybdenum are added in. Silicon or some other things can be added in as well. Tungsten, W, is a very common one. Manganese and nickel. Nickel and chrome are often brought in along with molybdenum to give different behaviors. So as we increase in the weight percent of how much of those alloys are present, nickel and magnesium, these two are going to drop the actual eutectoid temperature. So we add titanium, we add molybdenum, silicon, we add tungsten or even chrome, we improve these. So chrome isn't as aggressive as some of these other ones, but it has really high corrosion resistance, and so that's part of the reason why we use it in the alloys. Tungsten steels tend to be really, really tough stuff. And so depending on what we're trying to do with the steel, these other alloying elements can really, really help. So in terms of the weight percent, and then the weight percent of carbon, there's kind of a range. So the weight percent of the alloying element, we're going to have a change in as we go higher in the weight percent of carbon, we have to necessarily have a little bit less of the alloying element. If you think about it again in terms of trying to cram all different kinds of sizes of balls into a given box volume, right? You've only got room for so many. And if you start trying to replace some of the ping pong balls with golf balls or tennis balls, you're going to have a different amount of free space available within that network before you have to change the box that it's in, right? There's just limits on what's soluble. So these are different molecular sizes And so the relationship between something like carbon and nickel, because they're pretty close in general size, is a little bit more linear. Chrome, you can add quite a bit. It's closer to linear than not. Magnesium is sort of a linear relationship, but some of these, tungsten, very different behavior. You have to really take out most of the carbon in order to get the eutectoid. So what that does is it sort of shifts where this eutectoid is on the graph. So that'll be easier. That'll be easier if we go back here. Yeah. So this eutectoid point, what they're talking about is, instead of being somewhere around 0.76, just shy of 0.8, where it is now, so right in this region, as soon as you start adding these elements in, you're shifting it significantly. So any amount of titanium, and you're basically dropping down to something like 0.2. So you're kicking this eutectoid point over in this phase diagram to maybe, you know, way down here. And so you're changing significantly what the landscape looks like for the phase envelope. So we're not going to look at every single possible combination, but ones like nickel don't change it nearly that much. And some of them are kind of in between. So something like tungsten makes a pretty dramatic difference. Molybdenum makes a pretty dramatic difference. So tungsten is much more expensive of an alloying element than molybdenum is. And chrome is used typically in combination with nickel for some of that corrosion resistance. So there's a bunch of applications of those. But nickel has a less dramatic impact compared to some of the other ones. And silicon is kind of a fairly linear curve as well. So silicon is pretty neutral. It's good at absorbing some of the heat for materials. So there's different questions that come up. So phase transitions and transformations, things like, I guess, coal to diamond, same kind of chemical composition, basically different arrangement of atoms. And that's exactly what we're talking about in some of these. So this time temperature transformation and continuous cooling transformation diagrams, these are another piece that we're going to cover in order to understand better different temperatures at a given composition, right? So it's just this vertical line we're following. It's another to see what's happening in terms of the curvature of the materials. So this is where we start getting into these regions where we have perlite formed. So we go from austenite to perlite, or from gamma to perlite. So these are isothermal lines that we're going to be following, and you'll kind of see what that means. And as you go along in time, so these are typically log scale time graphs. A lot of reasons for that. It takes a very long time for something to cool from 700 C down to room temperature, just with simple air cooling. But the composition changes where this particular line starts to appear, where you start to get perlite formation. So this is very much dependent on what these things are. So the transition temperature is around 675 for austenite, because at the 700 you're almost in the austenite phase, which is stable. As you start dropping below that, you start crossing into, depending on how long, right? If you have a really, really long cooling time and it's not cooling off very much, like you just crack the furnace door open, you're going to pass through this at a very high temperature. And that's why this is called the unstable austenite phase. So you're going to have a longer period of transition through perlite, and then it'll cool down over a long period of time. So the shape of the curve that you take, how quickly you cool it down, is one of the things that can really make a difference in terms of how this behaves. So we're going to work with this example at 0.76 weight percent carbon, just because that happens to work right at the eutectoid point. We can much more easily know exactly what the temperatures are without having to interpret stuff on the line. So this is chosen for the sake of simplicity. So as this cools off for this given rate, you start out at 675 C, taking that transition. So that temperature happens here, somewhere just before 10 to the 2. And as this progresses, we fairly quickly transform the rest of that austenitic phase into perlite. So whatever is remaining. So this is what's referred to as time temperature transformation plots, or TTT plots. So this is something that I imagine you guys have some examples of in the homework for 10. I haven't gotten to look at that too closely yet, because I didn't even know I was going to be finishing out the semester for you guys until the Friday before I was leaving for a week for travel. And we just got back late last Friday night. So I've had lots and lots of time to cover this material. So this is the transition point at which it starts to form. This is the midpoint where it crosses this 50% line. And then this is the 100% where it crosses through the perlite phase. So this is held at a steady 675, and that's why this isn't a cooling curve yet. We'll look at some of those examples next. But if you hold it at 675 for enough time, the unstable phase converts into perlite. So if instead you change the shape of that cooling curve, instead of just being a straight line, if we start at the 727, so we're above in the stable austenitic phase, and rapidly cool to 625, what does that look like? So if we do a partial quench, or suddenly open the door and blast it with cold air or something like that, you're going to start at a different point here. So we have a different time for each of the beginning of perlite formation, 50%, 100% timeline, how quickly that happens, and you're into the perlite phase. So this is all austenitic, starts nucleation at this edge. We actually are getting perlite formation, and then 100% is full perlite formation. So then we have a couple other ideas. For instance, the non-eutectoid, we're going to have some different kinds of grains appearing. So this is a little bit more complex of an example. So starting at 1.13 weight percent carbon, what we've got is we've got austenitic phase boundary. So we have austenite plus cementite, so iron carbide, and then we have austenite and perlite both. So instead of just austenite and perlite from the last example, we're at a high enough composition. We are now hyper eutectoid. So this kind of steel is going to form what's called pro-eutectoid cementite, and that's what's going to be starting in this region. So the difference is we're right here on the phase diagram. So as we cool down from that 727 here, we've got both of these phases. That's what the cementite and austenite are telling us. So this is the same information on this graph. We're in that region where we're in the phase envelope for austenite and cementite. As we continue to cool, we're still on the same composition line, right? But this graph in terms of temperature is kind of like if we were to pull that 1.13% like a book off of a shelf, that's what this graph is. It's taking that information and turning it sideways, with the third dimension being time. So we're pulling the book off the shelf to look at the information that's in it with regard to time and temperature. And we can do that for any of these compositions. So these are just sort of like looking at the library shelf and seeing all the different composition books that are there. And these temperature time graphs are teaching us information about how it cools in this region, because depending on how quickly you cool, now you change what the compositions are. So you can figure out what the weight fractions are, but the composition and what those grain sizes look like, all of that depends on the time temperature graph. And that's why this is so important. So brainite is another example. So that's what the B represents whenever you see this on, or bainite, sorry, on the graph. We're still only about 1 coffee into today, which is a terrible life choice. Should be about 3 by now. So the elongated ferrite, or the elongated cementite particles in this alpha ferrite matrix are what we're referring to. So at that eutectoid composition of 0.76% carbon, you can see these two together. So this is something that can also happen, and this is below this temperature where we're only forming perlite. So this is something that happens down below this temperature range. So this is, what is that, 540 or so. So up here, you get 100% perlite. Down here, you get 100% bainite if you drop low enough in terms of overall temperature. So ultimately, it'll continue to drop lower and lower, and depending on what's happening with the curve, you get a couple other things. So spheroidite is important to understand. It's named because it looks like very small balls of cementite in a ferrite matrix. So this is what we do mechanically in order to do a process called spheroidizing the steel in order to make it easier to machine. So we'll talk about that in 11. But what that does is that allows for much easier grain boundary movements across each other. So it's just easier to work with, but it's not a very hard material at that point. So the spheroidite microstructure is important for processing of materials, especially because this is something that just facilitates working with them more easily. So the way that those are formed has to happen through diffusion, right? So think again about the stuff you've learned from chemistry about basically nature abhors a vacuum, right? Nature hates to have a vacuum. And what this does is it allows for, if you have an empty box on one side and you have a high concentration of things on the other side, and you alleviate the membrane or the barrier between the two, it wants to equally distribute things across the two spaces or the two volumes. It wants to fill the void. This is just what happens, right? Kids are a really perfect example of this being executed. Kids are highly programmed with the need to make sure that whatever an empty space is, if something is organized and clean, they have to make it messy because reasons. It just is, right? So nature abhors a vacuum, and diffusion works in metals just the same way. You just have to heat it up to what's called a spheroidizing temperature. And so we'll talk a little bit about that both here and in 11 as well, a little bit in terms of processing of materials. So you have to heat those at a temperature just below the eutectoid point for a long time. Why a long time? Because the more time you allow, the more diffusion it's going to happen at a given temperature, right? So you can hold it at a temperature for a given time, and you will get more and more and more formation of your desired grain structure as it cools. But you have to hold it at that temperature first. So there's a couple pieces that go into that. The driving force is, and it's kind of important to understand, it's reduction of the area between alpha ferrite and cementite. So it's surface area reduction is that driving force. So it's a thermodynamic force that's at play, but it's something that the material is trying to minimize the amount of energy that has to be stored in the material. Because if you have all sorts of jagged shapes and things, right, perlite has an extremely high interfacial area because of all of those folds and stacks and curves and things that are present. You have a really high interfacial area, so there's a lot of energy stored in the surface interactions there at the molecular level, which is another reason why it takes that much more force, that much more energy being transferred into the molecules themselves to actually make them move, right? So this is a really important concept.
Could you
So
go back 3 slides now? So
this one?
yeah, I understand how you get for eutectoid cementite on the right. That makes sense. But the left, how do you get for eutectoid cementite? I know it's the same composition, but I'm just not seeing it.
So yeah, on this one, because we're at so on the left side, we're still, so the proeutectoid cementite is referring to what's happening, the cementite that's formed basically above the eutectoid point or above that eutectoid temperature, right? So up here you have purely austenite. Down here, as you get just below this temperature, you've got cementite that's formed in both cases, because you have a combination. So this is maybe a little confusing on the label, because everywhere inside this envelope between the green line and the purple line, everywhere inside this region is actually cementite plus plus austenite. So what it's trying to represent here is, depending on how quickly you cool and how long it takes, you're going to have these two phases formed, even if the composition is lower, right? So even if we were on the left side, let's see if it's easily visible on this one. Not maybe, yeah, kind of visible here. It's the physical graph's a little bigger. So here, what we've got is, yeah, right here. So on the left side of the eutectic point, so if we're hypoeutectoid, so below the eutectoid composition, that's where you get still, as you're cooling on that curve, you're still going to get both carbide or cementite and our austenite. So it's a mixed phase here. And even as you drop down, you're still going to have the carbide. The things that you're going to have a little bit less of, just because of weight percents, are the perlite grains. So there's going to be some that are there, but it's going to be less on the left side, a hypoeutectoid steel, versus the right side. So does that make sense?
Yeah, that makes sense. I understand how to read those graphs. It's just what confuses me is that when I look at that graph to the left, that was 3 or 4 slides ahead.
Yeah. So
One more.
these are trying to represent.
There we go.
Yeah. This is just trying to represent on anything left of this purple curve is up here,
Right.
right? So up to about 900. So it's basically this graph starts right about here.
Okay.
So again, thinking about it like pulling a book off of a library shelf, as you drop down somewhere just a little bit above 800, just a little bit above 800 at this composition, you form. So here, this is probably 840 or so, 850, not quite 900, but pretty close. It's probably about 850, 860 at that composition. Anything below that temperature at any amount of time that you spend in that temperature, you're going to start to lose some of the austenite, and it's going to start forming this secondary phase, which is the cementite. So as you drop anywhere below that temperature, we start to get cementite in here. As you keep dropping in temperature, you start to hit this phase where you begin to do perlite, and that's below this 727. So as we drop down below, we're dropping, think of it at a specific point in time, wherever you are on the temperature curve, that tells you the same information that's here in terms of composition based on where is the eutectoid point for that alloy, right? We're just going like 100 million miles deep on iron because steels are so important. And so this is a great example to just kind of hammer into your heads. So anything below that eutectoid point is when we start to get not just we don't have the austenite continuing to form. The austenite converts into some ratio of perlite and cementite.
Okay.
So that's what this temperature graph is trying to teach us. So each of these are also a phase envelope, but it's a temperature time phase envelope instead of a temperature composition phase envelope. So it's still really important information, and there's a lot of information in this graph, even though it's like 4 lines, 5 lines, right? 4 lines and some dashes. Because this tells us a lot of information about what the material is doing as it cools, and the rate, how quickly it cools, we're going to find out in terms of the processing, especially later in 11. That's why all of this stuff goes together, and you sort of kind of have to learn all of it at once, but it's a ton of stuff. So that's why it's really important to try and get through as much as we can. It's also why I'm recording this, because expecting you guys to be experts on the iron phase diagram by the end of today is probably a bit of a stretch.
Always appreciate the recordings. Thank you.
So so this hypereutectoid example is just a higher composition, and we have more formation of perlite. So our the amount of time that we spend at a given temperature. So if we quickly cool something down to whatever this is, 520 or something, 515 C, you get this bainite formation. If you hold it at a longer time at a higher temperature, you'll get more perlite formation. So the rate at which we cool it, that's where some of this comes in. So spheroidizing takes something like a coarse perlite, and when you heat it up to a spheroidizing temperature, it comes over here to form spheroidite. So it's not just temperature, but it's also time in terms of the process. So again, we'll spend more time on that in 11, but it all goes together. If you spend more time at the higher temperature, typically you're going to get more fine perlite formation. So same composition, same molecules, different arrangement. If you cool it down to a much lower temperature, for the same composition, you get more of this bainite, which is a lot less zebra stripy. Maybe it's like maybe the spherodite is more like chicken pox, small grains of the cementite. Here it's a lot more thin, so maybe the bainite is a lot more. It's a lot more scattered and a lot more uniformly distributed to some degree. The fine perlite is often what we're going for in terms of wanting a really hard material. This material is going to be a lot softer, as is spherodite. Spherodite's probably going to be the softest of these two. Bainite's going to be somewhere in between. So depending on what we're trying to do with the steel, that'll change what we're trying to get in terms of grain structures. And we'll, again, talk more about some of the applications in the next chapter. So we start from austenite, and then depending on which path we take, dependent on the temperature and how quickly the temperature changes, slow cooling is going to give us this pro-eutectoid phase of perlite. So you're spending a lot more time at or above the eutectoid phase. You're going to get a lot more eutectoid. So that that's what this is referring to. So in order to form a lot of this eutectoid perlite, you're closer to that temperature. Moderate cooling is going to give you more bainite somewhere kind of in between, right? So this is different material in between. The rapid quench is what's going to drop you directly into another structure called martensite, and that's the really hard stuff. Martensite tends to be extremely hard but brittle. So when you see somebody like forging a blade for something, a lot of times they get it really hot, glowing red up in the austenite phase, rapidly quench it, typically with oil in order to prevent further scale formation and oxidation of the surface. It's not very often they do a water quench, but martensite actually gives a much more clear, hardened edge. So very, very hard surface, very inflexible, very brittle material, which then requires a second reheat in order to temper the martensite. So you're not heating it up to the same high temperatures, you're heating it up to a more moderate temperature in order to temper the martensite so that it's not as brittle. So this is why you'll see people talk often about a tempered steel. Typically that's one that's been hardened and then reheated in order to even out some of the grain structures and stresses that can come out of this. So it helps to kind of de-stress the steel and keep the small grain structures that are the martensite formation. So lots of really, really tightly packed zebra stripy looking grains. But this is the cost trade, right? So everything in life is a cost trade. Materials properties are no different, right? So the martensite temperature is higher. It's the curve is much more aggressive. It's very easy to spherodize. It's very hard to form martensite. Tempered martensite is a little easier once you've actually formed martensite correctly. Bainite is somewhere in the middle, fine perlite, and then coarse perlite. So inexperience at these processes is going to land you toward the bottom of these two, and your material strength, your hardness of that surface is not going to be as high. So really hard cutting tools and things of that nature almost always going to be alloys. There's almost always going to be martensite formation. So there's some really severe dramatic quench in temperature, often again in oil, which allows you to A, make sure there's enough carbon in the surface, and B, make sure that you're not oxidizing the surface. So it's a whole lot easier to do that. So there's a lot of precision needed for martensite formation compared to forming coarse perlite or something, which is if you heat it up and cool it, that's pretty much the way that works. So proeutectoid. Let's see. Yeah, questions?
Yeah, I had a question for the general trends for the different types of phase transformations. So for like the perlite, how does that affect whether or not what grows inside the grains? So like before, when we went to like I'm sorry, so in chapter 9, when we talked about the hypereutectoid and the hypoeutectoid, so for the cementite formed inside the grains, and then for the hypo, it was the ferrite that formed within the grains. How does that affect the ductility and the strength?
Yeah, so that's also part of the cost trade here in terms of like the way that the general trends behave. The general rule of thumb is the iron, the alpha phase, the ferrite is fairly malleable. So there's a lot of ductility in just the iron itself. This is part of the reason why it's fairly straightforward to forge wrought iron. It takes a lot of effort, but like you don't have to heat it up to 1400 or something crazy to be able to get it moving. You can go back and forth between this region, and as things are being heated, oftentimes you're going to end up somewhere in this region in terms of temperature anyway. So you're bouncing back and forth into these two. You're bouncing back and forth a lot of times over this eutectoid temperature in order to keep grains moving and maintain enough kinetic energy that the material is malleable. So the cost trade really is ductility. So the more cementite and the composition is very similar for cementite and martensite. The difference is I think we go into a little bit more difference or a little bit more detail in this part of the chapter. But the martensite is like really, really compact and condensed and a lot smaller grain size typically than something like the perlite is. So the perlite is less flexible than that alpha ferrite phase, but it's significantly more flexible than the martensite is. So the higher your hardness of the grains, the lower the ductility. And so the ductility is what's here. So the ductility is going down. Here the martensite is does not want to move, right? Whereas the spherodite, if you think about, if you punch your way into that box of ping pong balls, or if you jump into a ball pit or something, right? Like the difficulty of moving those balls out of the way is almost nothing, right? If instead you try to jump into a pit with a bunch of foam blocks, right, you're going to get stuck and stuff's going to drag on your jeans and you're trying to move around in it. And like, it's a lot of work to move those around. So the martensite, just in that same way, is a lot less ductile, but a lot higher in strength overall. So each of these terms, strength, hardness, all of these different terms, toughness, all have unique specific meanings within the context of materials, and it's important to understand how they're different. So a material can be very strong, like martensite, but not very ductile, which will make it more brittle, right? So it has a tendency to want to shatter or have a brittle fracture. There's other materials that are not very strong, right? They're not a very hard surface, so it wouldn't make a very good cutting edge, like spherodite, right? So think about how many times you've picked up a kitchen knife at somebody's house and tried to cut something with it, right? And it almost feels like you might as well be using a 2x4, right? You're just smashing stuff. You're not actually doing any cutting work, right? That's because that steel has been moved and abused. And so instead of having a sharp point, what you actually have is probably something rounded over, and it looks under a microscope almost like you're trying to cut something with the round edge of a wooden block, like a wooden arch block or something. It just doesn't work. Because those steels often, especially those grades of kind of inexpensive stainless steel, and even the country of origin changes a little bit the exact specific composition. So this is why there's a range on the phase diagram. American 4340 steel is going to behave better in an end application than a Chinese 4340 steel, because reasons that you'll learn in this class. But the key there is there's always this cost trade between ductility and strength. So strength is think like impact and cutting tools. This is where you need strength, things that you want to resist bending, you want to resist movement in the material under stress. That's where you need high strength. So when we say high strength steels, we're typically talking about ones that have a lot more martensite formation compared to pearlite. Does that make sense?
Okay. Yeah.
So it's a lot of information, and we're still going to talk some more about this and develop this out a lot more detail. But this is one of the places where we want to start to kind of get some ideas about how this works, right? So this isn't the last thing that we'll say about this, but quenching is important in order to quenching and the particular percent composition is important in order to get us the high strength materials, right? So this is in like the automotive industry, for instance. The reason this topic is so important is they're trying to build car frames and parts more and more, at least the frames, especially of trucks nowadays, out of high strength steel. So ones that have a lot more martensite, a lot less spherodite and coarse pearlite, because they're trying to apply loads now where you have sort of run-of-the-mill pickup trucks. If you can call $120 stinking $1,000 truck run-of-the-mill, which is economics is a separate lecture, so I'll leave that aside. But those trucks now are coming with towing capacities and ranges on the order of sometimes 24,000 pounds. That's enough to tow literally most people's houses, their entire dwelling. If it were on a trailer, these trucks could technically tow them. The idea of needing to tow an entire house is a little bit absurd, but it makes sense if you're hauling heavy mining equipment or something, which obviously everybody that buys a pickup truck is always doing. That's why they have the tow mirrors like always extended all the way out. Yeah, they have a joke about that in Texas. It's called all hat, no cattle. But that's one to look up for later. So the high strength steels are used in order to minimize the weight of the frame of something so that they can try and maintain a lower mass of the vehicle and increase the gas mileage by reducing the mass that it needs to keep in motion and accelerate. So trying to maximize economy while also maximizing work capability. But all those extra processes, all the difficulty of the tempering and all of those things greatly increases the cost of production. So there's a reason why all of this is the case, and there's a reason why a truck from 1973 is not the same thing as a truck built today, and why they're trying to use aluminum where they can in body panels, hoods, stuff where it's less important, and everybody's all hung up about, oh, the aluminum truck bed. Look, if you're trying to throw, 1,000-pound boulders from 20 feet up down into your truck bed, probably you shouldn't be using a commercial truck. You should be using a rock truck. But yeah, anyway, everything has an application, right? So what they're trying to do is maximize the materials, even down to the interior, because engineers' jobs is partly to minimize some of that weight, but not compromise any strength, right? So there's all these different things that go into this cost trade, but that's why it's important to understand what it is. So let's talk a little bit more about the Martensite specifically. So this is the transition from one type of grain structure to another. So did you guys talk about did you guys talk about the other alternatives, some of the hexagonal phases and some of the other things that form in terms of crystal structures?
I mean, we've talked about hexagonal close packed. So kind of.
Okay. So these Martensite behaves quite a bit differently. So even just looking at that structure compared to perlite, right? Where, again, think back to the deck of cards analogy. This is the deck of cards, because they share a lot of parallel planes. They're a little bit easier to flex, but they're very hard to tear and shear. This kind of cubic structure is like sharp needles and shards. And what that means is they are very rough. It's very hard to get them to rub past each other. They catch on each other and create a lot of different support points for impact. And they have support in that way, kind of in all three dimensions. So this is why there's also a lot of opportunities for carbon atoms to be fit into these phases, which is part of what creates the hardness of the material. So the way that this is formed is, instead of going for a long time at a higher temperature, we do a quick plummet in something like an oil quench down to around typically 100 or so below the bainite phase. Down here, somewhere around, don't remember exactly, 214, 220, whatever this is, you start getting a combination of the austenite and martensite. So in order to, that's the reason why forging materials, you typically are going to do some kind of plunge once you've got the rough shape made, and you're not going to do any more large movements. You're going to focus more on grinding and finishing, all of those things. This is a very rapid transition. There's no diffusion, and that's why it looks like it's just shards, right? Think about the same way that ice crystals form when it's really, really cold outside, right? You have moisture on the window, and it quickly freezes when it's exceptionally cold outside. Some of you that have been outside of Arizona actually know what frost is. It's this white stuff that covers surfaces sometimes. The same kind of crystalline shard formation happens for martensite, and this is why it's so hard, and it's easier for it to maintain such a sharp profile in a material. So the transition from this from the austenite to martensite, you get a mixture of these two. There sometimes are a couple quench stages, but it's usually very quick. It's usually just a couple of seconds, right? It's a handful of individual seconds. You don't leave it enough time. Like if you let it air cool for a little while and you take it, oh, I forgot to take the lid off or something, and then quench it, even if you only took a few seconds, you're going to drop through both the austenite and bainite phases. So this is why you'll see them take it out red glowing hot from the fire directly, right immediately, just seconds later, into the quench. And that's why you'll hear them, I don't know if the quench worked, or I don't know if I'm going to get the result I'm looking for. Because if it took too many seconds, you're going to drop through perlite and bainite phases. 4 or 5 seconds is enough to throw you off. So this is why tempering is also a higher degree of difficulty, not just a lower degree of ductility. It's very difficult. So it's rapid, it's diffusionless, and this is why we get these uneven shards of material. So it depends, and the percent transformation is only dependent on what temperature it was plunged to and how quickly it got there. So that's what will change the composition. So you might want to wait a second or two in some circumstances where you're still going to get martensite formation. But out here, if you've already formed a lot of bainite and it's taken you a long time to get it into a quench, you're going to compromise some of the procedures. So slow cooling will get you alpha and cementite. A quick quench will get you martensite. And this is a single phase. So this is a tetragonal. So this is, again, not even a hexagonal, but a tetragonal. It's leaves a lot of spaces for carbon to be solubilized. And just like in a solution, a liquid solution or something of that nature, there's a lot of options for where the carbon can be in that phase diagram. So the diffusionless transformation that happens is because you've got, it's a thing that happens, but that particular crystalline structure is only available to the material as an end state if you're above about this 0.15 weight percent carbon. So again, thinking all the way back to where we are on the diagram, it has to be above really this lower range where we consider it to be steel. Really has to be above this. Actually, I guess 0.15 is probably somewhere around here, above where we've got this alpha fraction, because this one is, I think, 0.022. So yeah, maybe it's actually closer to somewhere like here. The point is, you have to be able to form the austenitic phase in order to get there for any kind of martensite formation. The more carbon you have, the better you're able to reach that range. And this tetragonal phase, this tetragonal structure, really doesn't have a lot of slip planes available to it. Even some of the hexagonals still have quite a few slip planes available for the atoms to slide across each other. But this one just doesn't. In all 3 dimensions, it's sharp shards, and that's another reason why it's hard and brittle. So if you hit it hard enough with an impact, you're going to shatter the material along those fractured lines that are already there. So this is why that doesn't work really, really well. More questions?
All good so far.
Okay. Looked like Matthew or Vincent maybe had a question. Or they just fell asleep on their keyboard. Equal possibilities.
I think I might have pressed that by accident.
Yeah, it happens. Just like occasionally the mute happens, but at least when you're done, the recording will be of sufficient resolution that you'll be able to see it without needing glasses after the fact. So hopefully that'll be a slight improvement. So yeah, this particular body-centered tetragonal is going to be a lot harder and brittle, which is important. So the tempering is the step that brings you back to having some body-centered cubic ferrite in the overall phase. And this is an important aspect of getting a material that has a hard edge, but is not going to be as brittle. So it's kind of a compromise of those properties. So it's very, very important to understand what that looks like. So gets to be a little bit more complicated when we start adding in alloys. So we'll spend a little bit of time here. Specifically, this is going to be, we're not going to talk very much about titanium. We'll talk a little bit about magnesium. This one's specifically referring to manganese, molybdenum, silicon, nickel, chrome. All of these in different ratios are going to shift where these happen. So it's going to shift where the eutectoid temperature is still going to be the same because it's the same material. But now you can have some formation at higher temperatures or just below the eutectoid point. So depending on how long is spent there, you can start to have additional phases form. So it shifts much, much farther to the right, like 10 to the 3 instead of 10 seconds, 10 to the 3 seconds before you start getting a phase change. So these alloys are buying you additional time where you can have a quench happen. So it's a little bit more leeway, and this is part of the reason why these materials are like something like a chrome moly steel is really is typically going to be a lot harder than just a mild steel. So all of these things are going to shift where these different ratios are, and depending on how long you spend for a specific temperature, you're going to have different compositions. So here, sometimes it's going to be it's not always going to be perfectly clear where you're going to find the 50% line, for instance. It's trying to split the difference between the two, but it's not always going to look clearly that way. So here, a transition happens very slowly to have the ferrite plus perlite, and that's what the F is representing there. So we're going to look a little bit more about that process and what it looks like. So we have a couple other examples, so that aren't necessarily in in this, and so I think some of these will be a little bit helpful for you guys. So something like a tin lead alloy at 220C, we want to understand the relative amounts of each phase. We want to understand something about the what are the phases present. So at 220, right, we come up and we draw a line. I think I don't remember if she's actually got these represented. Yeah, so here we go. So we draw a line at 220. So we take a look at our R and S, and we can figure out what the phases are that are present. So here at 220, we're up into the liquid plus alpha region. So we're in this envelope. We have at 220, we have 46 for S and 17 weight percent. So this is our using our lever rule. And this gives us, so this gives us what we need for being able to calculate our relative amount of each phase. So remember that we use our one side divided by the sum of the two. So the 17 plus 46 to give us the weight fraction for alpha, and then what remains is what's going to end up in this case, it's going to be, the remainder is going to be liquid. And then down below that temperature is when we would see the alpha and the beta phase. And so we can similarly look at what each of those is. And so it can become a little hard to determine, but you have to do kind of a best estimate. So in the exams and things of that nature, it's really important to have a good straight edge and be paying attention to trying to keep it as vertical as possible when estimating where those tie lines are hitting for a given temperature. So I think she's got a couple, she's got another part of it. This one, let's see. No, I think this one's the same one repeated. There we go. So what we're looking for is this alpha. So our weight fraction of alpha is about 0.21. The weight fraction of liquid is about 0.79. So even when it's in a liquid alpha phase, this gives you the information on what portion of it is solid and what portion of it is still liquid for that particular temperature. So does this make sense how we got there?
That it do.
Okay. And I think she's got one or two more. So for a really high weight percent iron, very low weight percent carbon, so 0.4%, so it's a very mild steel, at a temperature just below the eutectoid, figure out what the following are. So the compositions, the amount of cementite in 100 grams of steel. So this is pretty straightforward. We're going to take those lever rules, apply them, get our weight fractions, multiply that by our total amount of steel, and figure out what the cementite is in terms of total grams. And then the perlite and the proeutectoid ferrite in the 100 grams. So as that cools off. So we'll take a look at the example. So just below this eutectoid point, so we have our R and our S. And what we determine out of these, because our R is down here at the very, very minimum range, so we have to estimate what these values are. Your weight fractions are going to be very, very small. So at this edge, we're down below that like 0.022 point. So it's really, really small. You're just going to have to do your best to estimate. The amount of carbide below this is the 6.7%. This is a portion of the phase diagram. We're not going to get into the rest of the phase diagram because yes, there is actually more than this, but we're not going to get farther than I think the 6.7% this semester. So the key to understand, because you start getting into like all kinds of charcoal and other weird phases at much higher carbon contents, a lot of weird stuff happens. A lot of other minerals. So the iron phase diagram with carbon turns into lots of other stuff later. But using the tie line, we can figure out that our weight percent here of the iron carbide is significantly higher at about 6.7 weight percent carbon. This alpha point is that 0.22, just barely below this eutectoid point. So the 0.22 weight percent is just a thing to kind of remember. So for this eutectoid, we're going to start here at C0, or for this subeutectoid point. We want to understand what those tie lines look like. So our difference between C0 and C alpha here for our R is going to be the difference between those two. So at 0.4, which is what was given to us here at 0.4% carbon, that's our C0. So 0.4 minus our 0.22, where alpha happens, gives us our R. So this is an important formula to remember as well, because this will give you the information that you're looking for. Same thing down here. The R plus S is mathematically the same thing as our C for iron carbide, the concentration for iron carbide, minus the concentration at 0, right? So this is mathematically the same thing, just an algebraic rearrangement. So our 6.7 minus our alpha of the 0.22 gives us our 0.057. So the weight fraction of the carbide, or the cementite, is very low, which is something that we would expect to see. We would expect that to be fairly low. So the amount of iron carbide in 100 grams is determined by taking that weight fraction, right? And we can easily find the alpha fraction by taking 1 minus this, and it's going to be the remainder. So majority of it is going to be ferrite. Very small percentage of it is going to be cementite. So in 100 grams times our weight fraction gives us our 5.7 grams. All right, so does this example make sense to you guys? Where are we on the grand scale of clarity? So there's like dirt with no water. There's like OG Gatorade flavors and lemonade and stuff. Then there's like Crystal Light. Then there's like flavored waters. And then there's like holy water is the very top. Where are you guys at on that scale?
Definitely holy water.
I think we're holy water.
Holy water.
Good. All right. So hopefully that's making sense.
Chocolate pie too. I mean, it's really
Chocolate pie. Okay. Well, chocolate pie is a little bit dense and unclear, so we got to keep going. So our C0 at this 0.4, remembering our alpha just barely below this point is 0.22 or 0.022. In order to figure out what the perlite amount is from this particular formation. So we're using the VX tie line. So if you see that in for this particular book, the RS and VX tie lines are above or below the eutectoid point. It's just a thing to remember as rule of thumb. The VX tie line for the second part, trying to find perlite. It's also used in the context of finding perlite. So it's important to know just kind of where those are. So this one is asking it just above eutectoid point. The perlite concentration is the same as the concentration for the austenite. So when we're looking at this side, we're at 0.057%. So we're a different weight percent here because when we take the difference between those two, we're looking at especially what the gamma phase is, which right at the eutectoid point is 0.76 weight percent carbon. So we take that into our calculation down here, and we say, all right, the difference between this and alpha, and the difference between our 0.4 source C0 and alpha, this gives us our 0.512. So our weight fraction of perlite actually ends up being pretty substantial. So a lot of perlite formation, not very much cementite left. We get a lot of perlite formed in that process. So figuring out the amount of perlite is that same 100 grams times perlite. And so same ratio, 51.2 grams of perlite to 100 gram sample at this particular composition. Right. So it's really not that fancy of footwork. It's just a good example of what that looks like, which will really help, I think, solidify some of the concepts. So this is some examples of the kinds of problems you're going to do on the phase diagram. So you're going to get lots of practice at this, and you're going to see this C0 minus C alpha, C gamma minus C alpha form a lot, because it's very useful for determining information about these tie lines. So there's a couple more that we have a little bit of time to get into, and then we can check for some further questions. So all of these microstructures are formed in different ways as a result of what path you follow in that time temperature transformation, or the continuous cooling transformation diagrams. So those are those temperature versus time graphs that we're looking at. The rate of cooling is what's going to tell us what the microstructures are. So in terms of like tests and quizzes and things, going to make sure that you're familiar with the effects of non-equilibrated cooling, and how that solidus line might shift in a phase diagram and things like that. So there's a couple things to keep in mind in terms of additional issues. Think about the process as you're going through, for instance, the eutectoid transformation. So the higher temperature, face-centered cubic, everything is sort of packed all together. It's spreading out a little bit molecularly. So it allows some level of diffusion for cementite and ferrite. So the cementite has some carbon in it, the ferrite does not. And so those carbon grains those carbon atoms in the actual cubic structure disrupt some of the spacing. And this is part of the reason why those regions don't move the same as the ferrite regions, where the ferrite regions are much more able to move across each other, different slip planes than what's contained within the cementite range. So there's a lot of principles that are happening, but it's all down to the structure of how the molecules are held together for the material. So the mechanical properties for non-equilibrated structures, are they more desirable? So let's start with that question. What do you guys think? Are they more desirable than equilibrium ones or not, and why?
It depends on what you're going for, whether you're going for strength or ductility.
Good. Yeah, that's what we're looking for. We want to oftentimes non-equilibrium structures are more desirable. But it very much depends on what the application is, right? Do you want something that's going to be able to be a hard cutting edge and cut into concrete? Or do you want something that's going to be able to flex and bend like a bridge truss for years and years, right? Those are two very different kinds of applications, where for that one, you probably want something that's more equilibrated and going to behave consistently throughout its life, whereas non-equilibrated won't necessarily have that same characteristic. So there's a lot of good things to think about there, and I think we're pretty close to the end. So the heating time, this is another principle that's important. It's something that you just need to have kind of in the back of your mind in terms of the way that things happen. So the fraction of transformation, you start getting some small amount of nucleation with heating time. At the halfway point, or T at T half, you get 50%. One is complete transformation to the austenitic phase. It takes a lot longer to grow the austenitic phase than it does to start that nucleation. So a lot of the times, this is why we have to heat something for a half hour, 45 minutes in order to get that formation to happen. We can't just stick it in the furnace, all of a sudden it reaches temperature and it's all equilibrated there. It takes time. So there is also a big temperature dependence on the transformation rate. So the recrystallized percentage, so trying to recrystallize things into the austenitic phase at 135 C, it takes a long time. So this is specifically in copper, so this is not steel, so you don't get super confused on temperatures. 135 C, copper recrystallizes pretty quickly in terms of number of minutes. As you drop that down, even just 20 degrees or 30 degrees, the time scales considerably. So this is a logarithmic scale. At 43 C, you will get there, but it's going to take a very, very long time. So the recrystallization rate, if you happen to come across that in the homework, again, I haven't seen what problems are on it yet. The recrystallization rate is 1 over the half time, or the time at 50%, whatever that time is. So with increasing temperature, the rate at which it recrystallizes increases. And sometimes the rates are so slow that you can't actually reach a true equilibrium state with the material. So this is another reason why bladesmiths don't always know, for instance, is that temper, is that hardened edge going to be as good as I hope it is? Well, I have to do all these processes and then test it at the very end to see if the material did what I wanted it to. They don't always know ahead of time. So that's why that's the case. Another thing that can happen is called undercooling. So undercooling is being below below this range for a much longer point in time. So the equilibrium is above, equilibrating conditions are above the 727. The undercooling or anything below that. So again, how much time does it spend at what temperature will help tell us whether or not it was equilibrated. So you have to cool below the 727 in order to in order for that phase transition to happen. So that's just a fancy name for the process that we're using to form these materials. And the reason the word undercooling is used there is you still have some gamma up until the point where you get true cooling in this process. All right. So a couple more details about the eutectoid transformation, what that looks like, and specifically the austenite to perlite. The grain boundaries, you'll start to see a little bit more clear distinction forming between the cementite and ferrite layers, and the perlite will grow linearly. So this is why it looks the way that it does, as it continues to grow linearly between those grain boundaries as the alpha forms. The reason being the carbon diffuses to these carbon-rich regions in order to minimize some of the surface energies between those phases. The carbon gets sequestered into these carbon-rich stripes. So it's a thermodynamic process, but perlite always grows linearly as those grains are cooling down. So the transformation rate changes with temperature, just like in other materials. But here, you can see that as the percentage of perlite, so it increases with the delta T, or the difference in temperature. So cooling it down to only 675 means it has a smaller delta T, and that goes more slowly, right? So if you cool it from 727 to only 675, it's going to go slower. If you cool it down instead to 650, it's a little faster. If you cool it all the way down to 600, it's a little faster. So the perlite formation happens much more quickly versus as the percent austenite gets reduced to 0. So the sharper the delta T, the bigger that temperature difference, the harder the driving force to change crystalline shapes, and the faster that process will go. The faster these guys will stretch out. So, but you still have to cool it a little bit slowly in order to get those phases to form for perlite, because of what we saw in those time temperature graphs. So the coarse perlite is at higher temperatures, and that's relatively soft. The fine perlite is formed at lower temperatures. That's relatively hard, and that's why tempering can be so tricky, as you can get some perlite and it's a kind of medium hardness steel, better than none, better than no change in hardness, but it's not a dramatic increase. So this is some of the things that we have to pay attention to, especially when we go to do those. So the cooling curves are more practical, but ideally, if you understand how to read those, the better off you are overall. So it's not necessarily all that hard. So the CCT, if you guys are asked to draw a CCT or something like that, that's these diagrams that we've spent so much time on today. The isothermal transformation is what it's formally called, but it's important to understand these are not all consuming in terms of, or all containing in terms of information. They are practical, but they have a lot of information contained, right? So there's a lot of people that would say the longer it takes you to fully comprehend a diagram, the higher your IQ might be, because you're trying to really understand everything that the graph contains. So if a picture contains something like 1,000 words, so they say, a graph likewise probably contains 1,000 words, and it's your job to be able to interpret out of that graph what all of the information is. So understanding what the cooling curve is and where it happens, how quickly that happens, tells you what percentage, what amounts, what types of formations happen in that time. So there's a lot of good information there. Fine perlite and coarse perlite, this is kind of the distinction between them. So if it transitions more quickly through this region, you're going to have finer perlite. So again, thinking back to the same principle as tempering, a slow cooling curve or a fully annealed, if you hear the term annealed material, we'll talk later about the annealing process, but you have a slower rate. This is a transformation that's happening during the cooling process, but it's spending more time inside that region forming perlite than this one is. This one's happening pretty quickly. So martensite transformation happens at the same temperature for both of these types of diagrams. So those will at least give you some idea what's happening. Again, the coarse perlite is at a higher physical temperature when it enters that boundary, that phase boundary. The finer perlite is at a lower temperature. So both temperature and time play a specific role in that. A critical cooling rate is here, where it just grazes that phase line for the transition to perlite and goes straight to martensite. So the critical cooling rate means anything below this, you form exclusively martensite. This is why forging, often when they're tempering and forging a blade or something, you want to make sure that it's inside this critical cooling envelope, because otherwise you won't get the control that you need. So there's a critical quenching rate. So if you don't have enough oil to absorb the heat from this sample to cool it quickly enough, it'll kick up into the martensite and perlite region somewhere in here. So this is why those are important. All right. So before we get too much farther, questions on this? You guys starting to sort of get a sense of what's going on there?
Yeah, all good.
I'd say so.
Okay. There is a lot of material there, and that was part of the reason why I wanted to make sure that we're getting recordings as well.
Professor,
But let me know if you guys do have questions.
I had a quick question for when we discussed whether or not non-equilibrium was more desirable than equilibrium. What did we mean by equilibrium and non-equilibrium?
Equilibrium is equilibrium. Think of all of the different types of atoms being evenly distributed across the whole of the material, and non-equilibrium meaning that you have pockets of higher concentration and lower concentration of things. So it's a way to describe whether or not something is uniform. So I'll go back to an example like this. So something like spherodite. There we go. Should be showing now. Something like the spherodite is something that forms, but over a much longer time. So it might be 24 to 30 hours at an elevated temperature to spherodize material. So spending 24 hours at a temperature allows this material to equilibrate very well. So it's very evenly distributed in its pockets. When we go back and look at martensite is the opposite of that, right? It's hugely uneven concentrations. It's very much non-equilibrated. And so it has all these needle-like shards that contribute to why it is as hard as it is. But it doesn't have the ability to move around, right? So equilibrated and non-equilibrated have a couple different implications, one of which is whether or not the material is going to move under force as easily, right? How much force it takes to physically move those grains past each other. In the case of martensite, extremely high energy threshold. However, the material is not tough, right? So toughness being the area under the stress strain curve. I assume you guys talked about toughness at least a little bit. Yeah. So these sharp needle-like structures mean that the material is not tough. It's actually very brittle. So it likes to fracture along a lot of those lines if you have a sharp impact load on the material. Right, so you wouldn't want a hammer with tons of martensite in it because you would go to hit something metallic and that hammerhead would shatter and explode on you. And that would be bad, right? So for a hammer, you maybe want something that is a little bit more even, like for instance, you might want something more like maybe a hypereutectoid where you've got some movement available. You've got a lot of resistance to the grains being crushed and things like that. But this is a much better material for a hammer than say the spherodized material, because if you smash this, the grains are going to be easily able to slide past each other or roll past each other because they're very sphere-like. So that material would not be a good choice for something that you need. If you are trying to reform it by force, then this is a great way to work with it, right? And that's why the answer to is an equilibrated material better than or more desirable than a non-equilibrated. The reason the answer is it depends is because if you're trying to work the material, if you're trying to work it, cold work it, if you're trying to hot work it, if you're trying to machine it, do a lot of things, right? It's a lot less wear on your cutting tools if you spherodize the material, because it'll just, the grains will separate more easily with less force, right? So you're not going to wear down your cutting tools as quickly because of the grain structure, right? Whereas in the martensite case, that's going to be a very hard material to cut, hard material to work with. This is why forged materials are much more expensive, right? This is why forged wheels on cars are much more expensive, because they forge the rough shape and then finish machining them. And so the cost can be many times what it is for a cast wheel, right? Because it's the process costs are sometimes 5 to 10x what they are for something like simple casting. So that should kind of help to give you a little framework to understand why the answer there is it depends.
Okay, yeah. So I think in class we said that, I don't know if there was a scenario given, but we said like the non-equilibrium was more desirable. But
For
it
a
just
lot of
depends,
material
like-
cases, yeah, it's more desirable to have non-equilibrium for end uses, because you want a material that's not going to be as easily deformed, right?
Mhm.
So think about something like a structural beam in a bridge, right?
Yeah.
Don't want a structural beam in a bridge to be fragile shards of something, right? Because and I forget, have you guys done, you haven't done tension testing in this particular class, right?
Correct.
Okay, you probably did at least one of those tension tests in 203, if you guys have taken that. I know some of you have. But what happens, especially with something like the high strength steel or high strength aluminum? Do you guys remember?
Okay, yeah, I understand. I was just a little confused on the equilibrium and non-equilibrium.
Yeah. So that's why those high strength materials, when they fracture, they have a surface that kind of looks like this, but on a bigger scale. So that's why the aircraft aluminum breaks with such sharp shards, is it's more crystalline structure like this. Same thing with the steel, whereas it looks a little bit more like this with the soft mild steel, and that's why it just sort of stretches and sort of pulls apart slowly, because they're going to be much more spheroidite like structure to it. All right. Other questions?
After this, I just had a question on the homework. I know you said you hadn't reviewed it, but I was hoping we could take a minute to discuss that later.
Okay. That'll work. Well, I think we're just about wrapped up, at least with the content for today. I know that's a lot of stuff, but we'll try and get you guys through 11 and get you farther into the material. We're still working on what the last lab is going to be, because it's probably not going to be the electroplating. We're actually probably going to swap that out. I'm thinking about a couple different options, so I'll work with Tyler to make sure you guys have what you need for that. But plan on Friday being you guys going into the SEM lab, so I'll try and be available for questions and things during that lab, because the SEM is something that I've spent inordinate amount of time doing. Lots of time in the smelly, damp cement dungeons. You guys have the luxury of being on the second floor, but that also gives you the complication of having a lot of extra noise in the image that's not necessary to have with an SEM. So we'll learn more about that on Friday. All right. So I think I'll stop the recording there and give you guys a chance to ask any additional questions related to class stuff, etc.